This will be a presentation overview for virtual reality viewpoint prediction. We'll take a look at what exactly it is, why it's important, some techniques proposed by others, as well as some results from my own attempts. Here's a quick guideline of what we will be covering. First, we'll be going through some basics for virtual reality, just what you'll need to be able to understand viewpoint prediction. Then we'll cover what exactly the problem is that we're trying to solve with this technique. Next, we'll describe exactly what viewpoint prediction is and how it solves that problem. We'll get into some techniques proposed by others, as well as my own attempts, as mentioned before. Virtual reality in the past 5 years has really taken the world by storm. Its major use for now is gaming, and the consumer market is what drives improvements and innovations for VR. VR tries to emulate the real world using very high quality 360 video. The technology is improving very quickly to the point where we're seeing huge leaps each year. It's really exciting to see what's to come. With new advancements like finger tracking, VR is starting to get to the point where it's becoming a very realistic simulation of the real world. Because of this, we're starting to see applications outside of gaming now too, such as education and training for things like surgery and pilots. Due to this jump in quality, we're seeing a big jump in popularity as well, with orders for almost all headsets being backlogged for months now, despite the ridiculous price of new units, but older units are much less now. Luckily, I was able to get my hands on a unit early, and I can really attest that the quality is just as good as it looks. Well, actually I'm very lucky because I got a second one for the purpose of testing various units. So as I mentioned before, VR uses high quality 360 video. This means that any optimization methods directed towards 360 video are also applicable to VR. The reason this presentation is directed to VR and not just 360 video will become apparent when I give the problem description after. In order to describe what a viewpoint is, it makes sense to connect it with the context of how 360 video works. 360 video uses an omnidirectional camera to record 360 degrees around the camera for each frame. The frame produces as shown on the right, and of course with many VR games this frame is produced virtually without a camera. The 360 frame is then projected onto a sphere where it looks like a recognizable 2D image. The user's frame of reference is then put inside that sphere. So then what the user is seeing is the inside of that video frame. Typically a device used for VR or 360 video has curved lenses that look like this, where the user looks through them and it covers most of their field of view. The part of the sphere that the user sees through the lenses is shown here. Specifically, those rectangles on the left and right show the entire field of view of the user projected onto that sphere. What those rectangles represent, or in other words, everything that the user is currently seeing, is the viewpoint. Although to be more specific, it's the coordinate representing the center of that field of view rectangle. Knowing what this viewpoint is about all the background info you'll need to understand this project. So what type of problem does VR face today? What challenge is preventing further advancement, innovation, and mainstream adoption? For the purposes of this project, it's the major increase in computation time and bandwidth. 360 video, on average, takes up about 4 to 6 times the bandwidth and computation time of regular 2D video. On top of this increase, there's also a major constraint for VR. About 90 video frames per second must be maintained to prevent motion sickness in the user. Most virtual reality developers determined that about 90 frames per second matches how the real world feels. If the frame rate is any lower or stuttering occurs or halts, then what the user is seeing will not match what their brain thinks they should be seeing, and this will induce nausea or motion sickness. It should be noted that these 2 points can be considered to be the same problem from our solution standpoint. It's just that solutions to computation time help on the consumer end, and solutions to bandwidth will help rendering by the provider. The main problem from a consumer standpoint for virtual reality is the cost of entry. On top of the hundreds or even thousands of dollars that a user spent for a VR headset, look at the minimum system requirements required to run a regular VR application. 12 gigabytes of RAM, a GTX 1060, you're going to need another $1,000 just to be able to run VR. You need the expensive hardware to be able to handle the high computation time and bandwidth while maintaining that 90 frames per second. This brings us to our solution. We have to optimize 360 video because 360 video is the major workload for virtual reality. Also note that by optimizing 360 video for VR, we also allow for increased complexity for future applications with current hardware. This is why a solution directed to consumers also works for providers. To find this optimization, we look at how VR currently handles 360 video. Remember that 360 video takes up about 4 to 6 times the computation time and bandwidth in comparison with 2D video. This large increase is a result of rendering the entire 360 degrees around the user, but perhaps we can reduce that. Looking at this figure again, VR tech today renders that entire sphere. Isn't this extremely inefficient? Why don't we just render exactly what the user is currently seeing, or their viewpoint? Clearly, this would massively decrease render time and load, about 80% to be precise. However, this solution actually doesn't quite work, and I'll quickly show why it's not really realistic. Here's a quick demonstration of how 360 video is rendered for VR. Firstly, the next full 360 frame is generated and rendered. Next, the user's headset senses where they're looking at and generates the current viewpoint. And lastly, the portion of the video frame represented by the given viewpoint is then streamed to the headset screen. Remember this is being done 90 times a second, so 90 fully 360 rendered frames, 90 provided viewpoints, 90 streamed portions, so you can see why the workload is so high. So if we try to apply what I mentioned before and only render what the current viewpoint is, then the cycle looks like this now. It may look fine at first glance, but the problem is actually apparent here. Rendering the viewpoint portion in this case takes too long. There's too much of a delay between providing the user's viewpoint and streaming that portion of the video back, which is latency. Looking back at the current model for VR, there is no latency between providing the viewpoint and streaming that portion, or virtually negligible latency. If there's too much latency, then the user's current actual viewpoint will have moved on from that provided signaled viewpoint, which means what's being streamed to them is not their actual current viewpoint, or not close enough at least. This disconnect between what the user's brain is expecting to see from the current viewpoint and what they're actually being streamed will induce more motion sickness than even a lower frame rate, so this is actually the worst case scenario. Looking back at the current model, we can actually still apply the idea of only rendering the current frame. What we can do is predict the next viewpoint and only render that portion. If we can perfectly predict the next viewpoint, then it's essentially the same solution as before, but this time with no latency, making this the ideal solution and giving us about 80% savings. To make predictions for each next frame, we use some sort of a function from current viewpoints. This is the model for viewpoint prediction. The rest of this presentation will be describing the various techniques for viewpoint prediction. However, first I'd like to go through a very basic example. Here we have shown a 360 video sphere in full. Imagine that we cut the sphere in half relative to where the user's current viewpoint is. We can predict that for the next frame, the user's current viewpoint will still be within that half. Therefore, we only need to render the front half. Even though this is a very basic model, it seems reasonable because I very much doubt that a user can turn their head and see the back half within 1/90th of a second. You can see that even with a model as simple as this, basically a thought experiment, we can save 50% of the rendering. And now we're going to move on to some much more sophisticated methods which will save hopefully much more than 50%. The first viewpoint prediction method we'll discuss is arguably the most popular, but what I also consider to be the most successful. The paper shown here is one of the most cited for this topic, so we'll go through it as an example for this method. The proposed method is prediction based on head movement. Specifically, they try to predict the next movement using multiple past user movements. In this case, they split the movement data into X, Y, and Z. They decided to test each angle separately, so each angle has its own prediction. Next, they predict the deviation for each of these angled predictions, so in a sense, it's an error prediction for the original prediction. I highlight this because it's very important for this specific method, and many other similar studies don't do it. Lastly, they generate the user's next field of view, or the next predicted viewpoint, which is the culmination of this method. The generated field of view is some function of the deviation and original prediction. In this study, they just add the deviation to the prediction, and it produces good results. I'll go more in depth into this study, but just know that most head movement based prediction methods are very similar to this guideline. Here are how the angles are split up specifically. So pitch, yaw, and roll represent the X, Y, and Z angles. The Y angle represents looking left and right, which is by far the most common movement among users. The X angle represents looking up and down, which is the next most common. and the Z angle is tilting left and right, which is the least common by far. The study also determines how much users shift these angles within 0.2 seconds, which is the same as their recommended prediction look ahead. The results stated that for 90% of the time, the X, Y, and Z angles are within 15, 35, and 8 degrees respectively, so that's for the next 18 frames. These angles give an idea of what the maximum prediction for a generated field of view should be. Next, I'll describe the prediction models typically seen used for this method. The first attempt is just a naive model, which uses the current viewpoint as the prediction for the next viewpoint. This model was intended to be a base control model, so not to perform very well, but surprisingly, it actually does perform very well, likely due to users looking the same direction much of the time. The next model is a linear regression model. I'm not going to cover the implementation of it here because linear regression is not the best model for this purpose. Just know though that the prediction error for it is about twice as low as the naive model. The neural network is the best model for all prediction lookaheads and all angles. Explaining how a neural network works would take much too long for this presentation, but I will list the properties they use or the specific implementation they did. So again, they trained the data for X and Y separately. They also used 50% of the data for training, and I believe it should be more like 75 or 80%, but perhaps they got better results with 50. 3 layers and 5 hidden neurons is also very arbitrary. They likely got best results with that in this study, but pretty much every study decides on different numbers. The prediction lookahead is the varying variable here, and it's pretty important, so I'm going to describe it in the next slide. The prediction lookahead is essentially how far into the future we try to predict, or how much data we try to predict. It's also how much of the past data we use to predict the next frame, so essentially how many past frames do we use for the next prediction. A smaller lookahead is more accurate, so it's easier to predict where someone's looking half a second later versus 10 seconds later. However, larger lookaheads save much more computation and bandwidth, which I'll describe with the next few points. For example, this study recommends a lookahead of 0.2 seconds, which at 90 frames per second, which VR runs at, comes to a lookahead of 18 frames. So essentially this means that we predict which location to render once every 18 frames, or 0.2 seconds. So after the neural network model predicts the next viewpoint, or the angle changes, a field of view is then generated to be rendered. Pictured here is the generated transmission area, or the next field of view. So essentially, the center portion is the original prediction, and the outer portions are the error predictions. By adding the error to the original, then we generate the full field of view. Looking back at this figure to make things more clear, we can assume that the rectangle represents the user's current field of view, or viewpoint. Let's also assume that the time window is 0.2 seconds. So if the model predicts that for the next 0.2 seconds, the user's field of view will be within this circle, then we only have to render this portion of the sphere for the next 18 frames. Again, if we can make a perfect prediction, then that circle will be the same size as the rectangle, giving us about 80% savings as mentioned before. In practice though, this is just not possible, due to the randomness of human head movement. One thing I haven't mentioned yet is the amount of computation required to do the prediction in the first place. So there are multiple trade-offs to consider when optimizing a solution for this method. The results showed that for every 0.1 second the lookahead is increased, there's about a 15 to 20% decrease in computation. This is the trade-off between accuracy and computation, because conversely, decreasing the lookahead increases accuracy, but also increases computation time and bandwidth. That decrease in accuracy is shown here, where that same 0.1 second increase is about equal to a 10 times higher failure ratio. The failure ratio is essentially the amount of missed pixels by the prediction. So missing 1 out of 100 pixels in a prediction would be a 1% failure ratio. This study suggests that an acceptable failure ratio is at most 0.1%, or a prediction accuracy of at least 99.9%. There's always the option to allow for an increased failure rate. This would decrease the quality but also decrease computation by a lot. 0.1% is just suggested because it makes it indistinguishable from current practice. So the most optimal result tries to minimize computation while maximizing accuracy. The optimal result in this study for a 0.1% failure rate is given by the 0.2 second lookahead. It gives an average render reduction of 75%, and 45% of the total average bandwidth is reduced. This is actually the most significant result. What this means is that 45% of the total computation cycle for virtual reality is reduced by this single optimization. The next viewpoint prediction method we'll discuss is tiling prediction. For the purposes of demonstration, I'll use this paper as a reference for the implementation and results of this method. We call this method tiling because it divides the 360 video sphere into a number of tiles or rectangular segments. A larger number of tiles will increase accuracy, but a smaller number of tiles will lessen computation. This study suggests that 72 is a good balance. Each tile is then one-hot encoded relative to the field of view. One-hot encoding in this case means that tiles within the FOV are assigned a 1 and tiles outside the FOV are assigned a 0. For a good visualization, I'll refer back to this figure. So again, tiles within the field of view are assigned a 1 and tiles outside are assigned a 0. Now, there's not 72 tiles here and they're not of equal size either, but it's a good visual for this method. For this prediction model, they determined that a 2-second look ahead is actually sufficient. This is a lot more than the previous model, but it makes sense because this method is a lot less robust. Predicting the general field of view based on large tiles is less intensive than getting the exact angles. The data inputted into the model is a 72 by n one-hot matrix. So that's 72 tiles, and n is the frame look ahead, so the 2-second look ahead multiplied by the frame rate. And again, the matrix contains ones and zeros, which represents each individual field of view. And of course, the neural network is the model of choice. Again, I'm not going to describe how it works, but I will list the properties here. They elect to choose 9010 for training testing, and the model that worked best was the multi-layered long short-term memory model. What the prediction model outputs are probabilities, specifically the probability for each tile to be within the next field of view. The idea is to select the tiles with the highest percentage of being within the next field of view, and then generate an entire field of view around each of those tiles. So looking at this example, we select the 2 tiles with the highest probability of being within the next field of view, the ones the arrows are pointing to, and then we generate an entire field of view around both of them, and that double field of view is sent as the prediction. This figure shows selecting 2 tiles, so selecting more tiles would increase the accuracy, but it would have a lot more redundant rendering, so it would increase computation. The number of tiles they select for this study though varies depending on which application they're measuring. Generally though, it's about 4 or 5. That's actually something I forgot to mention, was that for this study they have varying results because they tested the data separately for each application. By doing so, they were able to categorize each application. So what I mean by this is that, while always maintaining a 95% accuracy minimum, they were able to attain a 43% render reduction for high-speed movements within an intensive application. For the intensive application though, they also separated high-speed movements from normal speed movements, and for normal, they attained about a 56% reduction. And for non-intensive programs, they were able to attain a 70% reduction, and for that they felt no need to separate the movement at all. So this method doesn't quite perform as well as straight-up predicting head movement, but it's much less computationally intensive, which is why it might be preferred in some cases. So those are the most commonly proposed methods. So what did I do? How can I build on them? How can I improve them? What should I do? Well, my first thought was to try to improve each of those methods as much as possible. So optimize it as best I can to decrease rendering while maintaining quality. So first I looked at improving the first method, head movement prediction. The only thing that stood out to me from that first study was that their data set was relatively small. So I thought, let's just do the exact same method on a bigger data set, see what happens. So that's what I did. A neural network, 3 layers, 5 hidden neurons, 0.2-second look ahead, and about 20% lower than their... Okay, well, what do I try next? I considered how they implemented their neural network next. So they chose 3 layers, 5 hidden neurons, but I have a different data set, so perhaps a different number of layers and a different number of hidden neurons would get me a better result. So I tested out a large variety of numbers for layers and hidden neurons, and what I found is that nothing ever improved by more than 1%. So for the sake of consistency, I kept going with 3 layers and 5 hidden neurons. So the difference has to be in our dataset. So I decided to select 153 random people from my 36,000 to match their dataset size, and I tested it on them. A little surprising, but 62% bandwidth reduction, while less than their 75, is much more than my 56. I tried it with multiple random batches and it came out to about the same. You would think that more people would make things more consistent, but I guess that's not the case here. Seeing this, I thought, what would happen if I go lower? So I started lowering the people while testing. 10,000, 56%. Pretty much the same as 36,000. 1,000, 59%. Maybe there is something going on here. 100, 62%. 10, 65. 3, 68. 1? Now, as amusing as this trend looks, you can't really use it because with that low amount of people, you can't create a consistent model. Now, the main reason I think that their results were so much higher than mine was because their entire dataset consisted of new VR users, and it's very likely much easier to predict a new user in VR than one who's experienced. But perhaps this result for one person might be somewhat useful, like maybe each individual headset predicts that specific user's movements, and it could work that way. Next, I looked at trying to improve tiling prediction. I could actually recreate the original results seen in that earlier study because I had access to the same dataset. But there's been so much work done on tiling prediction that it's hard to find somewhere to optimize that other people haven't already tried. However, there is one thing I did want to try. What would happen if I increase the number of tiles? Is there a tile number that's better than 72? Cutting into more segments would be more accurate, right? So why not increase the number of tiles from 72 to 1 million? Well, actually my computer couldn't handle 1 million at all, so let's try 1,000. The motivation for this idea was that they never gave any reason for choosing 72 tiles. However, my results for 1,000 kind of prove that 72 is a good choice, because even with this massive increase in computation, it resulted in a 5% render reduction. It's just not worth it. After considering each method individually, I thought, how could I combine them together? It's interesting because predicting head movement is kind of a human element, and predicting tiling is kind of a non-human element, so somehow combining them together might give an interesting result. The first attempt is just to add them together. So essentially a naive model where we treat both methods equally, and whatever they both predict, we render. I test this on the intensive application from the tiling study because that makes this a worst case analysis. As expected, the render reduction is 40%, which is considerably lower than each of the methods individually. It makes sense that the reduction is lower because even if the accuracy is higher from using both, we're adding the errors as well. So the idea I had was to assign weights to each of the methods, which represent how much to rely on each of them. So how do I achieve this? I mean, this seems kind of arbitrary. Well, the idea is that the weights represent the failure ratio of each method. So we always want to maintain a 0.1 total failure rate, but we can use a combination of the two where one is allowed to have a higher failure ratio while the other one is lowered, for example. If they are both weighted at 1, then that would be the previous case where we just add them together. Remember that increasing the failure ratio for either of them vastly decreases computation, so if a good combination of the two gives a good result, then it's by far the best method here. Interestingly, the result is kind of as expected. It's to completely rely on head motion prediction. There was basically a linear relationship between the weightings for tiling and head motion. What this means is that the higher the weight was for head motion and the lower the weight was for tiling, the better the render reduction was, topping out at 56% when the weighting was fully on head motion prediction. If I have to draw a conclusion from this specific case, it's that head motion prediction seems to perform better than tiling. In general, we see this supported by multiple studies as well. The only upside I see to using tiling would be the much lower computation required to do it. Typically though, if you have a computer that can render VR, you should be able to do the prediction as well for head motion. Tiling seems better suited for low-end mobile devices that stream VR from a provider. It's easier to implement and the computation is much faster, so maybe that's the case where it works.